Hello students, today we are going to learn about invertible functions, or we call it bijective functions also. Okay, so let us start. A function f from a set non-empty A to another set non-empty B is said to be invertible or bijective if it is both 1 1 and onto. If it is both 1 1 and onto, all the functions which are 1 1 and onto are also called bijective. And when a function becomes bijective, if function becomes invertible, so there will be another function running from range to the domain of f, and that function will be called f inverse. Okay, f inverse of x, or simply f inverse. Okay, so this is the basic definition. Okay, now we are going to learn a few properties, a few results which we are going to use when we are going to solve the problems. Okay, so first thing, before going into the properties, we must notice that this f inverse is never going to be equal to 1 by f. Okay, f inverse is not going to be equal to 1 by f. In fact, f inverse is another name of another function running from the range of f to domain of f. Okay, so this thing has to be keep in mind. Okay, few properties, as I said, a few properties to be discussed. Properties means these are a few results, standard results that we are going to remember. F inverse for a function f, if it exists, is unique. Okay, f inverse, if it exists, is unique, means there cannot be more than one inverse for a simple same function, for a single function. Okay, so f inverse is unique. Okay, the next thing we must know, an alternative definition of f inverse for a function f from a to b. If there exists another function z from b to a, this one was running from a to b, and this must run from b to a, such that z of f is equal to f of z. Both are identity function. Okay, then we say f inverse to be equal to z. Okay, this is an alternative definition to this. Okay, for a function f from a to b, if there exists another function z from b to a, satisfying z of f, composition of z and f and z both are same and both are equal to the identity function, then we call z to be the inverse of f. In fact, both are inverse of each other in this case. Okay, z is the inverse of f, f is the inverse of z. Okay, the next thing we need to know, z of f whole inverse is equal to f inverse of z. F inverse of z inverse. Okay, f inverse of z inverse. This order in which they are composite will change. Okay, f inverse of z inverse. And next, these are few standard results that we must know before we go and solve some problems. Okay, next, graph of f inverse of x is the mirror image of the graph of fx in the line y equal to x. So if we know the graph of one function, suppose e to the power x, we know the graph of e to the power x is like this, right? So inverse of the graph of inverse function will be the reflection of this graph on the line y equal to x. So if we take reflection, simply we will get something like this. Okay, and this is nothing but ln of x. Okay, this one was y equal to e to the power x. Okay, so if we know the graph of one function, the inverse function graph can be drawn by taking the reflection on the line y equal to x. That is what this result is telling us. Okay. The next point is fx and f inverse of x intersect, if at all. Okay, it is not that always they have to intersect. If they intersect, then fx and f inverse intersect, if at all, at y equal to x. They will intersect in the line y equal to x only. The point of intersection will always lie on the line y equal to x. That is what this point is telling us. Okay. Okay, if we know this much, we can do many equations in fact. Okay, so before going into find out the inverse, we'll just try to discuss the steps involved in finding out the inverse of a function. Just taking one simple question. Okay, suppose we have to find out the inverse of this function r to r. Fx equal to 3x plus 5, it is given, it is defined in r to r. So step 1 will be write y in place of fx. Step 2 will be find x in terms of y. Okay. Step 3 will be swap the values of x and y. That is, in place of x you write y, and in place of y you write x. Then in place of y simply write f inverse. That one will give us the inverse all the time. Okay. So these are few steps involved in, we'll take as standard whenever we are finding out the inverse, along with these properties. Okay, we'll club them whenever the need of the problem will arise. Okay, first question here, find the inverse of the function fx equal to log of x plus root over x square plus 1 to the base a. A is greater than 0 and is not equal to 1. Okay, so the solution will go like this. The first step was we'll take y in place of fx, so let y equal to log of x plus root over x square plus 1 to the base a. Okay, so we'll use logarithmic property, so it will become a to the power y will be equal to log of a to the power y will be equal to x plus root over x square plus 1. Now the second step was to find x in terms of y. So in this particular function it will be very difficult to find out in general. So what we'll do, we'll just try to rationalize it, so that we'll get this x square minus x square plus 1 by x minus square root of x square plus 1. Simply multiplying and dividing by conjugate of this. Okay, so we'll be getting minus 1 upon x minus root over x square plus 1, which can be written as 1 by root over x square plus 1 minus x. So this is the value of a to the power y. Okay, let us try to write a to the power minus y. Therefore, a to the power minus y will be equal to, it's reciprocal, right? To the root over x square plus 1 minus x. Now check, a to the power y from here and a to the power minus y from here. From these two equations, if we subtract, that will give me x. This 2 will be cancelled, so we'll be getting the value of x. That is what we are looking for, x in terms of y. So what we'll do, therefore, if I am considering this one to be equation 1 and this one to be equation 2, so what we'll do, 1 minus 2 will give us 2x will be equal to a to the power y minus a to the power minus y. So x in terms of y will be a to the power y minus a to the power minus y by 2. What was the next step? We'll swap x and y. So y will be equal to a to the power x minus a to the power minus x by 2, and in place of y we'll write f inverse of x. Therefore f inverse of x will be a to the power x minus a to the power minus x divided by 2. Again, that will be, since if fx equal to this, x if x is less than 1, x squared if x is lying between 1 and 4, 8 root x if x is greater than 4, then we have to find out the inverse of x. The solution will go like this. We'll make 3 cases out of it. Case 1, when x is less than 1. So what we'll get, fx equal to y equal to x. So x in terms of y will remain the same, so this itself will give us the f inverse. So f inverse of x in this case will be equal to x only, and the case is when x is less than 1. So case 2, when x will be lying between 1 and 4. So here we'll remember that x is always positive, so we'll take y equal to x squared, x in terms of y, so x will be equal to plus minus of y. As x is always going to be positive, so there is no point in taking the value of y which are negative, so x will be equal to, so x will be plus minus root y. So x will be equal to square root of y. Okay, we'll swap. So we'll get y equal to root over x. Now when x is lying between 1 to 4, we have to check where y will lie. When x is lying between 1 and 4 and x is positive, so y will lie between 1 and 16. So this is true for all x lying between 1 and 16. So ultimately f inverse of x in this case will be root x if x is lying between 1 and 16. Okay. Case 3, when x is greater than 4. Okay. So y equal to 8 root x. 8 and root x both are positive, so y will be always greater than 0, that we have to remember. Now we'll find x in terms of y. So we'll be getting x equal to y squared by 64. Okay. Swap x and y to get y will be equal to x squared by 64. So this is the f inverse, but we have to check where the value of x lies, right? So x is greater than 4. Okay, so y squared by 64. Let us check. When x is greater than 4, x equal to y squared by 64 is greater than 4. So y squared is greater than 64 into 4 means y is either less than minus 16 or y is greater than 16. But y cannot be lesser than minus 16 because this is the first line I told you. Y cannot be negative, so this is neglected. So y is greater than equal to 16. So that is here. Y is greater than equal to, strictly greater than 16. We have swapped, so y greater than 16 will become x greater than 16. So x greater than 16. So ultimately f inverse of x will club all these 3 cases to get from the first case x when x is less than 1, then we'll get root x from the second case when x is lying between 1 and 16, and in the third case we'll be getting x squared by 64 when x will be greater than 16. So this is the answer. This is given fx equal to x modulus of x, then find f inverse of x. So this can be broken into two parts. Fx equal to x squared if x is greater than equal to 0, minus of x squared if x is less than 0. Okay, let us solve it graphically. Fx equal to x squared, so x squared graph will be something like this for x greater than or equal to 0. Okay, so this is y equal to x squared. And for x less than 0 it is minus x squared. So for transformation fx gone for minus fx. Okay, now we need the inverse of this. So already we have learned if we know the graph of fx, f inverse x graph will be the reflection of the same graph fx on the line y equal to x. So let me draw y equal to x, this one is y equal to x. So we'll take reflection. So reflection will be for x greater than 0 it will be this, and for x less than 0 it will be this. This one will be the graph of f inverse of x. Okay. Again, so what will be this graph? This one will be y equal to positive square root of x, and this one was y equal to minus x squared. So this one will be y equal to negative square root of negative x. Right? Therefore, f inverse of x will be equal to 1 positive square root of x if x is greater than or equal to 0, and this one negative square root of negative x if x is less than 0. So this is the answer. If fx equal to e to the power x minus e to the power minus x by e to the power x by e to the power minus x, then find f inverse of x. So what we'll do, just we'll put y in place of fx, e to the power x plus e to the power minus x, e to the power x plus e to the power minus x. Now to solve this x in terms of y, let me write e to the power x equal to t, so that I'll get y equal to, this one will become t plus 1 by t by, sorry, this one is minus t plus 1 by t. Upon taking LCM, we'll be getting t square minus 1 by t square plus 1. So x function, t is a function of x now. So we'll try to express t in terms of y, right? So we'll cross multiply y t square plus 1 is equal to t square minus 1. So t square y minus 1 will be equal to minus y minus 1. So t will be equal to plus minus of square root of y plus 1 upon 1 minus of y. Okay, what is t e to the power x? E to the power x we know it to be always positive, so there is no place of negative sign out here. So t will be equal to positive square root of 1 plus y by 1 minus y. Okay, we'll write the value of, rewrite the value of t. E to the power x equal to 1 plus y by 1 minus y to the power half. X in terms of y, so ln of half ln of 1 plus y upon 1 minus y. Again, x in terms of y, then what we do, we swap. So y, x and y, ln of 1 plus x upon 1 minus x, and this gives us f inverse of x. The question says us, if f and z be two linear functions, such that for all x, z of f and f of z are identity functions. Okay, and if f is 0 equal to 1 and z0 is also equal to 1, we have to find out the value of f1. Okay, and this question can be done in many ways. The easiest way would be this: z0 is given to be equal to 1. One thing we have to notice, z of f and f of z both are given to be identity, matlab f and z both are invertible and both are inverse of each other. So z of 0 equal to 1 implies z inverse of 1 will be equal to 0. Okay, from here we'll get. Similarly, f inverse of 1 is also equal to 0. We'll try to find out this too, and we are going to use whenever it is required. Now, z of f. Suppose we'll find out z of f1 because we are ultimately looking for 1. The value of x is 1, right? So let us try to find out z of f1. And according to this, both are identities. So z of f of 1 should be equal to 1, right? So z of f of 1 should be equal to 1. So f of 1 should be equal to c inverse of 1, right? C inverse of 1. Z inverse of 1 is 0. So f1 is nothing but 0. Let fx equal to 2x minus x square for all x less than equal to 1. Find the roots of the equation fx equal to f inverse of x. Okay, so here we are going to use that concept where fx and f inverse of x intersects. We need the common points, right? We have to solve this equation, means we have to find out the points which are common to both the equations. And we know that fx and f inverse of x, if they intersect, we have to find out those points only where they are going to intersect. They intersect at y equal to x. So this is what we are going to look for. Okay, go for graphical approach. Okay, we'll try to draw the graph of it. It's concave down, passing through origin. Okay, we'll try to find out this highest point. Minus p by 2a minus 2 by 2, that is minus p by 2a. So 1 and minus d by 4a, that is b square. B square is 4 minus 4 is 0 by 4 d by 4a, 4 minus 4 minus 1. So 1 comma minus 1. So this point is 1 comma minus d by 4a plus 1 comma 1. Okay. Now this function is defined for x is less than equal to 1. So this part of the graph is not required. Otherwise f inverse will not exist because it will no longer be 1 1. This point is 1 comma 0. Okay, we need f inverse of x. This is the graph of y equal to fx. How to draw the f inverse x graph? We'll take reflection on y equal to x. This one will be something like this, right? Okay, so both are intersecting at fx, f and f inverse of x are intersecting when x equal to 0 and x equal to 1. So the solution is the root of the equation. Roots are x equal to 0 and 1. Otherwise, The second method can be done like this: fx equal to f inverse of x. They were intersect at y equal to x. So ultimately we'll get fx equal to x will be the solution. So fx equal to x minus x square equal to x. From here also we are going to get x equal to 0 and 1 as the solutions. Okay. Okay, we'll go for the next question. Next question, this is find the real roots of x square plus 2ax plus 16 equal to minus a square root of a square plus x minus 16. Okay. Okay. Let me take y equal to fx equal to the right hand side function minus a plus square root of a square plus x minus 16. Okay, and we'll try to get the inverse value of f. Okay, so let us go for it. The idea is, if I can show this any one of this function to be the inverse of the other, I can write the solution as solution to be fx equal to x. That is the idea. Okay, so y plus a will be equal to root over a square plus x minus 16. So we'll whole square y plus a whole square plus x minus 16. So y square 2ay plus a square plus x minus 16. We'll write x in terms of y. So x will be equal to y square plus 2ay plus 16, which can be written as y plus a whole square. Only keep it like this. Okay, so is it the other one? Yes. If we'll swap x and y, what we'll get? Y equal to x square plus 2ax plus 16, which is nothing but this left hand side equation. So f inverse of x is x square plus 2ax plus 1 by 6. So ultimately this equation is looking like f inverse of x equal to fx. Okay, so we know that f inverse of x equal to fx means they intersect at y equal to x. So by virtue of that, fx will be equal to x is the solution. So we'll get x square plus 2ax plus 16 is equal to x. So x square plus twice a minus 1 into x plus 16 equal to 0. So we'll find out x minus b is this, plus minus root over b square 1 minus 2a whole square minus 4ac, that is 1 by 4 by 2a. Now I have to check for which value of a. This one is real. So a is given to be 0 to 1 by 4. So 2a will lie between 0 to half. So half square. Even if it is half, then also it becomes 0. Otherwise it will become always positive. So for all values of a, all given values of a, x, both the values of x can be taken. So we'll have two solutions and given by this. Okay, so that's the answer. Go for the next question. It is given fx equal to greatest integer function of x minus 1 plus fractional part of x to the power greatest integer function of x. X is belonging to the open interval 1 and 3, 1 comma 3. Then we have to find f inverse of x. Okay. So since greatest integer function is involved, so let me split this interval into two intervals. One is 1 to 2 open and 2 to 3. So we break into two intervals. Okay. So when x is belonging to 1 to 2 open. Okay. So fx will give me, this one is giving me greatest integer function of x minus 1 plus fractional part of x in 1 to 2 upper interval. This greatest integer function will, let me write one more way. So we have used the property now. So greatest integer function in this interval will be 1 minus 1 plus fractional part of x, greatest integer function value in this interval is 1. So ultimately we'll get fractional part of x. So let me call it x minus ZIF of x. Okay. Again, this ZIF of x in this interval is nothing but 1. So ultimately I have got fx to be equal to x minus 1. Okay, so what will be f inverse x then? F inverse x will be simply x plus 1 when x is lying between 1 to 2. So x plus 1 will lie between, x is lying between 1 to 2, so f inverse x will lie between 0 to 1, right, from here. Okay, so this is the first case. Second case, when x will lie in 2 to 3 interval. Okay, so fx is ZIF of x minus 1 plus fractional part of x whole to the power of ZIF of x. Okay, so greatest integer value in this interval is 2 minus 1 plus fractional part of x is, this one is again 2. So we'll be getting fractional part of x whole square, that is nothing but x minus ZIF of x whole square plus 1. Okay, now y equal to this. So x minus ZIF in this interval is 2, so x minus 2 whole square plus 1. So what will be f inverse x then? F inverse x will be y minus 1 square root, that is y and x will swap. So x minus 1 square root plus 2. Okay, now we have to find out which interval it will lie, y will lie. So x is lying between 2 and 3. So where y will lie? 2, it will become 1, and 3, it will become 2, right? 1 to 2. In the interval, x is lying between 1 to 2. Okay? Therefore, finally, f inverse of x will club this both result, x plus 1 when x is lying between 0 to 1, and 2 plus root square root of x minus 1 if x is lying between 1 to 2 is the answer. So for the solution, since it is bijective and fx is a cubic function and it has got 3 real roots, it is they are saying. Now 3 real roots, if a function is having 3 real roots, so the ideal condition is this. Okay, it has to intersect the x-axis at 3 points. Now since this function is given to be bijective, so in no way it can happen so, because otherwise the function will no longer be 1 1. At many places we are going to get same value repeated. So in order to be bijective, this given cubic function must have single repeated root, only one root. It can intersect only at one point. Okay, so it must have a repeated root. Okay, so that is what we have to analyze from this question. Okay, so let us solve it. Fx equal to 0 will have 3 roots and since the function is bijective, so we must get x cube plus ax square plus bx minus 8 has 3 roots. All 3 of them are identical. Okay, so let me take alpha to beta root. So it will be x minus alpha into x minus alpha into x minus alpha. Okay, I hope you have understood this point. Okay, so let us solve it now. X minus alpha whole cube. So x cube minus 3x square alpha plus 3x alpha square plus alpha cube is equal to this. So we'll equate the coefficients. X cube is already cancelled. So we'll equating coefficient will be getting alpha cube equal to minus alpha cube, sorry. Alpha cube equal to 8. So alpha equal to 2. Equating the coefficients of x square, we'll be getting a equal to minus 3 alpha. That is, a will be equal to minus 6, and equating the coefficient of x will be getting b equal to 3 alpha square, that is 3 into 4, 12. Therefore a plus b will be equal to 6. So this will be the required answer. This question is telling us let fx equal to x square minus 2x for all x belongs to R, and let f is running from minus infinity to a close to b close to infinity, where a is the largest number for which f is bijective. We have to find the value of a plus b. Okay, so we'll take x equal to x square minus 2x minus 1. So x minus 1 whole square minus of 2. So let us solve it graphically. Let us draw the graph of it. X minus 1 whole square minus 2. So it will come down here. X equal to 1, y equal to minus 2. So the graph will be like this. Okay, now come to this part. F is running from, the domain is given to be minus infinity to a. Okay, so both part of the graph of the vertex, we have to analyze which part to be taken. From this both the parts, one part has to be taken according to the question. It is starting the domain, the values of x is starting from minus infinity to a. So definitely we have to remove this part of the graph. Okay, so according to the question, the part of the graph is now this. Okay, again, this one is nothing but y equal to fx equal to x minus 1 whole square minus 2. Okay then, now what is the value of a? Minus infinity to, the value of x is running till 1. So the value of a is 1. It is the value of x. And corresponding value of y will be here. It is starting with b, that is b, the value of b has to be equal to minus 2. Therefore a plus b has to be equal to minus 1. So that is the answer for this question. Okay, fx equal to 3x minus 2 and z of f inverse of x equal to x minus 2, we have to find out the value of zx. We'll try to use that property here. Z of f whole inverse is f inverse of z inverse. Okay, so we'll do that, but before that, fx equal to 3x minus 2. So clearly f inverse of x will be equal to x plus 2 by 3, right? Now z of f whole inverse is given to be x minus 2. So f inverse of z inverse of x is given to be x minus 2. So f inverse of x is this. So what we'll get? We'll get simply z inverse of x plus 2 upon 3 equal to x minus 2, right? So z inverse of x will be getting as 3x minus 6 minus 2, that is minus 8. Okay, therefore zx has to be equal to inverse of this function. So inverse of this function will be x plus 8 upon 3. Okay, so here we have used this. Also we have used this. Z inverse of whole inverse is z. Okay, and let fx equal to x square minus 2x plus a whole into a plus 1, where the function is running from a close interval to infinity to a close interval infinity. And if one of the solution of fx equal to f inverse of x is 5049, then the other solution may be. This is an MCQ, and this is more than one correct type of question. Okay. Okay, we'll try to simplify this, and we'll try to get the inverse of it, because we have been asked to solve fx equal to f inverse of x. So let us first try to solve y equal to fx and try to get the inverse of it. X square minus 2ax plus a square plus a. So y will be equal to clearly x minus a whole square plus a. So f inverse of x will be plus minus root over x minus a. Now it is given that domain and codomain both are starting with a, so the negative sign will not have any impact. So we'll be going for positive value. F inverse of x is this. Now all we need to solve is fx equal to f inverse of x. So fx simplified form is this. So we'll solve. Now solving fx equal to f inverse of x, we'll get x minus a whole square plus a is equal to a plus root over x minus of a. So a cancels, so we'll be getting x minus a whole to the power 4 equal to x minus of a. So ultimately we'll be getting x minus a whole cube equal to 1. So x equal to, not that. X minus a whole cube minus 1 equal to 0. So we'll be getting x equal to a or x equal to 1 plus a. So one of the solution is given to be 5049. So if a equal to 5049, then the other solution will be 5050. So one answer is this. Again, if 1 plus a equal to 5049, then a will be equal to 5048. So there are two answers actually, either this or this. So 5048 and 5050 may be the two solutions of fx equal to f inverse of x. Okay, thank you, thanks for watching. Okay, thank you.